Good day, everyone. Today we'll be taking a look at the Cambridge Assessment International Education Further Mathematics, that's 9231, paper 32, which is the mechanics, the further mechanics paper for October-November 2022. Some background information on this paper. The threshold for an A for this paper was 26 out of 50, which is roughly 50% of the paper. So it's a fairly low grade threshold, I would say. But hopefully this video is helpful and you all will or should be scoring considerably higher than this grade boundary in your actual exams coming up. So we'll jump straight into question 1, which deals with circular motion here. It tells us that a particle of mass m is attached to one end of a light inextensible string of length a. The other end of the string is attached to a fixed point O, which is held taut with P making an angle alpha with the downward vertical, where cos alpha is 2/3. The particle is projected perpendicular to OP in an upwards direction with speed root 3 ag. It then starts to move along a circular path in a vertical plane. Find the cosine of the angle between the string and the upward vertical when the string first becomes slack. So, as with a typical mechanics question, a lot of information has been given here. The best thing to do first is always to draw a diagram to try and visually understand what's going on in the little situation that they've given to us. So we have this particle, there's this fixed point O, and we can have this as our reference position O. And it says that the particle makes an angle alpha with the downward vertical such as this. They told us that the particle is projected with speed v equals root 3 ag, and we want to find the cosine between the string and the upward vertical when it first becomes slack. So the particle is going to move from P to some new position, say Q, such that its angle here will be something, let's say, theta. Now, to approach this question, and it's pretty standard how we approach questions just like this, we use the conservation of energy, which says that the initial potential energy plus the initial kinetic energy must be equal to the final potential energy plus the final kinetic energy, where the initial energies are taken at the point P and the final energies are being considered at the point Q. So if we consider the potential energy at the point P, the potential energy of the particle at P is given by minus mga cos alpha, and its initial kinetic energy is plus a half mv squared, which in this case becomes plus 1/2 m, and v squared simply becomes 3ag. When it moves up to the position Q, its potential energy will now be given by mga cos theta, and its final kinetic energy will be given by a half mv squared. Now, what's useful here is we can try to work out an expression for v squared, which we would then use later in our calculation. Now, we know that cos alpha is equal to 2/3. So we could make this as minus mga 2/3 plus 1/2, well, plus 3/2 mga minus mga cos theta is equal to 1/2 mv squared. If we simplify this up, we should get 5/6 mga minus mga cos theta is equal to 1/2 mv squared. We can divide throughout by m and then multiply by 2 to give 5/3 ga minus 2ga cos theta is equal to v squared. Now, what we do is we consider at Q. So if we resolve at Q, we will find that the tension plus mg cos theta must be equal to mv squared on r. And in this case, the radius of our circle is the length a. Now, because the string is going slack, it means tension must be 0. And this leads us to mg cos theta must be equal to m Well, we can cross multiply one time by a, so we get AMG cos theta is equal to m, and we can now substitute our expression for v squared, which was 5 on 3 GA minus 2 GA cos theta. If we divide throughout by MGA, like so, we get that cos theta is equal to 5 on 3 minus 2 cos theta. And this leads us to 3 cos theta is equal to 5 over 3. Therefore, cos theta is equal to 5 over 9, which is the required angle asked for in the question. So pretty standard question, and most questions are approached in a manner identical to this. Question 2 deals with centers of gravity. So this question tells us that a uniform lamina in the form of a triangle ABC, in which angle B is right angle, AB is 9A, and BC is 6A. The point D is on BC such that BD equals X. The region ABD is removed from the lamina. The resulting shape ADC is placed with the edge DC on a horizontal surface, and the plane ADC is vertical. Find the set of values of X in terms of A for which the shape is in equilibrium. Now, the important thing to recognize here is what is the equilibrium condition. And the equilibrium condition here, if we consider the center of gravity of this particle, we could denote it x bar and y bar. In this case, only x bar would be of significance. X bar has to be such that it falls within the lamina. If the center of gravity goes outside of the lamina, the object will topple. So for this case, it means that if this is x bar, it should line up at the very least with this point here. So it means that the center of gravity x bar has to be greater than or equal to the distance x. So it can be here or anywhere inside, but it cannot fall outside the lamina. Otherwise, the object topples. So what we can do here is use the area of the lamina to help us work out what the center of gravity x bar would be. So the area of triangle ABC is given, of course, base by height on 2, which in this case is 9A by 6A on 2, which is 27A squared. The area of our triangle ABD is also base by height, which is 9A by X all over 2. And the area of the resulting lamina ADC, so area of ADC is, of course, just the difference here, which is 27A squared minus 9AX on 2. Now, we can set up an equation to work out our center of gravity x bar. So for our triangle ABC, because it's a right angle triangle, x bar is 1/3 of the distance BC. So in this case, we can say that 27A squared by 1/3 of the distance BC, in this case, becomes 2A, minus the area of ABD, which is 9AX on 2, and its center of gravity, its horizontal center of gravity, its position will also be given by 1/3 BD, which in this case is X over 3. And this must be equal to 27A squared minus 9AX on 2 by x bar. Now, what's important here is to keep track of the algebra. What we can do here, we can now simplify this, so we can get 54A cubed minus 3AX squared all over 2 is equal to 27A squared minus 9AX on 2 by x bar. Now we can solve for x bar to show that x bar will give us 54A cubed minus 3AX squared on 2, all divided by 27A squared minus 9AX on 2. And using the condition we discussed before, x bar has to be greater than or equal to x. Following on with this algebra, this should give us 54e cubed minus 3 on 2 ax squared is greater than or equal to 27a squared x. 27a squared x minus 9 on 2 ax squared. Minus 9 on 2 ax squared. So from here, notice that we could divide throughout by a and get rid of the a altogether. But even before that, we could multiply throughout by 2. So we could multiply throughout by 2 and then divide throughout by e. And doing this should give us 3ax squared minus 27 a squared x plus 54e cubed is greater than or equal to 0. Right, and once we obtain this equation here, we can simplify this. So we will end up with 3a sorry about that, we'll end up with 3a. Right, and once we end up with this equation here, we can bring the minus 9 on 2 over, so we'll end up with 3ax squared minus 27a squared x plus 54a cubed is greater than or equal to 0. We can divide throughout by a rather, and this will give us 3x squared minus 27ax plus 54a squared is greater than or equal to 0. Now, there are two ways you can do this. If you can see the factors for this, go right ahead and factorize. But if you have a little bit difficulty with the factorization process, that's not an issue. To do this, you can simply just apply the quadratic formula on this and you will get the answer. So if we consider this up here, so up here, the quadratic formula becomes minus b, which is 27a, plus or minus the square root of b squared, which is 27a all squared, minus 4 by 3 by 54a squared all over 6. This becomes 27a plus or minus 9a all over 6. Right, which then simplifies to give us that x, and remember this equation is solving for x, it gives us that x is equal to 6a or x is equal to 3a. So from regular maths, if we have 3a and 6a, this is a minimum type quadratic. We are looking at here's our regions. So it means that x must be greater than or equal to 6a, x must be less than or equal to 3a. This first condition cannot be true because the length of the lamina is only 6a. So it means therefore that x must be less than or equal to 3a. And strictly speaking, it must be greater than or equal to 0. So this here is your solution, your range of values of x for which this object would remain in equilibrium. So again, not too much of a difficult question. The difficult part is perhaps just keeping track of the algebra involved. Question 3 deals with elastic strings. So this question tells us that one end of a light elastic string of natural length A and modulus of elasticity 16 on 3 mg is attached to a fixed point O. So off the bat we can say that this is some fixed point O and we have this string here attached to a particle P of mass 4m. So this is P and its mass is 4m. And they tell us that the 4m is attached to the other end of the string and hangs vertically in equilibrium. Then they tell us that another particle of mass 2m is attached to P and the combined particle is then released from rest. The speed of the combined particle when it has descended a distance 1/4 a is v. Find an expression for v in terms of g and a. So first things first, at equilibrium, we know here that the tension, so if this is, so this weight is 4 mg must be equal to the tension. So the tension must be equal to 4 mg. From our studies, we should know that tension is given by lambda x over L, which is on MF19 is equal to 4 mg. We know that lambda is 16 on 3 mg and L is E. So this becomes that 16 on 3 mg by x all over A is equal to 4 mg. And from this, we should be able to get that x is equal to 3/4 A. So this is the extension when the particle is at equilibrium. So this here, we have to let it be our reference position. Now, how do we go about with the rest of this question? What, again, is important to observe or to recognize is that this is also a situation where we have to use conservation of energy. And what we would use here is the fact that our initial potential energy plus our initial kinetic energy plus our initial elastic potential energy must be equal to our final potential energy plus our final kinetic energy plus the final elastic potential energy. So what is our initial potential energy? So we can let the equilibrium position be our zero reference. So in this case, our initial potential energy will be 0. The initial kinetic energy is also 0 because the particle is initially at rest, because it's in equilibrium. But what is our elastic potential energy? Our elastic potential energy is given by the formula lambda x squared on 2L. And in our situation, this would be 16 on 3 mg. Our extension we just found out to be 3/4 A, all squared, all divided by 2 times the unextended length E. This, in turn, is equal to our final potential energy. Now, what is our final potential energy? Potential energy is, of course, given, well, gravitational potential energy is given by mgh. The combined mass of the particle now is 6m by g by h. Now, what is h? The particle has descended a distance of 1/4 A. So this means that this will become A over 4. Now, because the particle is descending, it's losing gravitational potential energy. So we include a negative sign here to signify that it is losing gravitational potential energy. Right? Its kinetic energy will be given by 1/2 mv squared, which is this, and our new elastic potential energy is given by lambda x squared onto A. Now, what is our new extension? Our initial extended length was 3/4 A, and now it has descended a distance of 1/4 A. So the new total length is actually A. So this becomes A squared all over 2E. And this is our energy equation that we have set up. And all what is required to do is simply to make V squared the subject of the formula from this. So tidying this up, we'll get that 3 mg on A on 2 is equal to minus 3 on 2 mg A plus 3 mv squared plus 16 on 6 mg A. What we can do from this is cancel out our m terms, and this then becomes that 3 on 2 GA plus 3 on 2 GA minus 16 on 6 GA is equal to 3V squared. Simplifying this further, this gives us that GA on 3 is equal to 3V squared. Therefore, GA over 9 is equal to V squared, and V will be the positive square root of GA over 9, which is root GA over 3. And this is our expression for V, in terms of V and G. So again, this question just required us to use our basic formulae from elastic strings and springs, and the most important part is setting up the energy equation here, which is pretty standard, similar to question 1. In a similar idea to question 1, our energy equation here is just modified a bit to include the elastic potential energy term, right? So the initial potential energy, gravitational potential energy, plus the initial kinetic energy, plus the initial elastic potential energy must be equal to the final gravitational potential energy plus the final kinetic energy plus the final elastic potential energy of the system. And this enables us to very quickly find an expression for V in terms of A and G, which is asked in the question. Right. So now, looking at question 4, it tells us here that a particle P of mass 5 kilograms moves along a horizontal straight line. At time t seconds, the velocity of P is v meters per second and its displacement from a fixed point O on the line is x meters. Right, so we have the particle something like this. We have a fixed point O and at some point in time t, it's here at position P. The forces acting on P are a force of magnitude 500 on V newtons, 500 on V newtons in the direction of OP, and a resistive force of magnitude 1/2 V squared newtons. When t is 0, x is 0, and v is 5, find an expression for v in terms of x. So the first thing we can do here is write an expression for the net force on the object, which in this case will give us 500 over v minus 1/2 v squared, and this is equal to mass by acceleration, and our mass is 5, so this is equal to 5e. And this is from Newton's second law. Now, the question asks us for v in terms of x. We know that if we have displacement, dx dt gives you the velocity, and similarly dv dt will give you the acceleration. However, we cannot use this because this gives us v in terms of t, we want v in terms of x. So what we need to remember here is that acceleration is also given by v dv dx. And this equation becomes 500 over v minus 1/2 v squared is equal to 5v dv dx. What is useful here now is to combine this as a single fraction. And if we do this, you end up with 1000 minus v cubed all over 2v is equal to 5v dv dx. And what is required now is to perform variable separation of this differential equation, and this gives us that dx is equal to 5v all over 1000 minus v cubed all over 2v dv, which of course transforms to 10v squared all over 1000 minus v cubed dv is equal to dx. Once here, all what is required for us to do is now to integrate both sides of this differential equation. The question is, how do we go about doing that? So if I write here integrating both sides, the right hand side becomes very easy because that will simply become x plus c. So we get the integral of 10v squared all over 1000 minus v cubed dv will be equal to x plus c. How do we integrate this left hand side? What we need to recognize here is this is of the form k f prime x all over f of x, right? Where the numerator is the differential of the denominator, and this becomes ln f of x plus c. Now, if we differentiate the denominator, we get minus 3v squared. So if I put minus 3v squared here, that's not what our initial question has. Our initial question has 10v squared, so we need to multiply by an additional term of minus 10 on 3 to ensure that the numerator is the exact differential of the denominator. So integrating this will give us minus 10 on 3 ln of 1000 minus v cubed is equal to x plus c. And now we can use the initial conditions of when x is equal to 0, v is equal to 5. And from this, we solve for c, and c becomes minus 10 on 3 ln 875. 1,000 minus 5 cubed is 1,000 minus 125, so ln 875. So our expression, therefore, becomes, carrying on here, the expression becomes minus 10 on 3 ln of 1,000 minus v cubed is equal to x minus 10 on 3 ln 875. What we can do here now is multiply by minus 3/10, and this will give us ln of 1,000 minus v cubed is equal to ln 875 minus 3/10 x. We can carry this ln term over and combine to give ln of 1,000 minus v cubed all over 875 is equal to minus 3/10 x. Removing the ln gives 1,000 minus v cubed is equal to 875e to the minus 0.3x. Therefore, v cubed is equal to 1,000 minus 875e to the negative 0.3x. We want v in terms of x, therefore v is equal to 1,000 minus 875e to the minus 0.3x, all to the power of 1/3. And this is our expression for v in terms of x. Fairly straightforward. Then part B asks us to state the value that the speed approaches for large values of x. So directly from this expression we just found, we can see here that when x goes to infinity, that is when x gets very large, e to the negative 0.3x would also go to 0, which means that this entire bracket term here will simply go to 1,000. So v actually goes to 1,000 to the power 1/3, which is the cube root of 1,000, which is 10 meters per second. Right? So pretty standard and straightforward question here. Moving on to question 5, which deals with projectile motion. It tells us here that a particle P is projected with speed u meters per second at an angle theta above the horizontal from a point O on a horizontal plane and moves freely under gravity. The horizontal displacement of P from O at subsequent time t seconds is given by x, and the vertical displacement is respectively given by y. They want us here to show that this is the equation of trajectory. So sketching the story, and this is something pretty standard as well. If we have O, the particle is undergoing projectile motion, it's being projected at speed u at an angle of theta. Now, if we consider firstly the horizontal displacement, or rather the horizontal component of the velocity, resolving here, we can get horizontal and vertical components of the velocity. The horizontal component of the velocity we should see is given by u cos theta, and the vertical displacement of the vertical component of the velocity is given by u sine theta. Right? Now, if we consider the horizontal displacement x, this will be given by ut plus 1/2 at squared. However, in the horizontal direction, there's no acceleration. So it becomes that x is equal to ut. And the u in this case is the horizontal component of the velocity, which is u cos theta times t. Likewise, if we consider the vertical displacement, y will be given by ut plus 1/2 at squared. Now, acceleration here, because it's moving under gravity, the value of acceleration is given as g. And because we are going against gravity, the particle is being projected upwards. The particle is being projected upwards, but gravity acts downwards. The value of g is negative g. So it becomes ut minus 1/2 g t squared. And u is again the vertical component of the velocity. So y equals u sine theta by t minus 1/2 g t squared. Now from this expression, from the horizontal equation we have, we can solve for t, and t becomes equal to x over u cos theta. And we can now substitute that into our vertical displacement. So y becomes u sine theta by t, which is x over u cos theta, minus 1/2 g t squared will become x squared all over u squared cos squared theta. And very easily now, this becomes y is equal to x tan theta minus gx squared on 2u squared. 1 on cos squared is sec squared theta. But remember that 1 plus tan squared theta is equal to sec squared theta. And if we replace that here, we get the equation of trajectory in the form that they want, which is x tan theta minus gx squared on 2u squared into 1 plus tan squared theta. Right? Part B tells us that in the subsequent motion, P passes through the point with coordinates 30, 20. Given that one possible value of tan theta is 4/3, find the other possible value of tan theta. So what is required here now is just using the equation of trajectory that we would have just derived. So this becomes our x value and this becomes our y value. So substituting into our equation, we would know that 20 is equal to 30 tan theta minus g x squared all over 2u squared into 1 plus tan squared theta. Now the question also told us that one value of tan theta is 4/3, so this will enable us to solve for our unknown u squared. So tan theta is equal to 4/3. So this gives us 20 is equal to 30 by 4/3 minus this whole thing, 10 by 30 squared on 2 simplifies to 4500 on u squared into 1 plus 4/3 squared is 16 over 9. And we can now solve this very easily for u squared, and we should obtain that u squared is equal to 625. And all what is required now is to now use u squared as 625 in our initial trajectory equation and now solve for tan. So again, we will get that 20 is equal to 30 tan theta minus 4500. 4500 again is the value of 10 by 30 squared on 2, which is gx squared on 2, right? All over 625 into 1 plus tan squared theta. This becomes 20 is equal to 30 tan theta minus 36 on 5 minus 36 on 5 tan squared theta. Rewriting this, we get 36 on 5 tan squared theta minus 30 tan theta plus 136 on 5 is equal to 0. If we multiply throughout by 5, this becomes 36. This becomes 36 tan squared theta minus 150 tan theta plus 136 is equal to 0. We could divide this by 2 to make it a little bit simpler. So we get 18 tan squared theta minus 75 tan theta plus 68 equals 0. And factorizing this expression, we get 3 tan theta minus 4 and 6 tan theta minus 17 is equal to 0. This, of course, gives the first value of tan theta as 4/3. This gives our second value of tan theta as 17/6, which is what the question asks us for. Right? Moving on to question 6. This question tells us now that a light inextensible string is threaded through a fixed smooth ring R, which is at a height h above a smooth horizontal surface. One end of the string is attached to a particle A of mass m. The other end of the string is attached to a particle B of mass 6/7 m. The particle A moves in a horizontal circle on the surface, and B hangs in equilibrium below the ring above the surface. Right? When A has constant angular speed omega, the angle between AR and BR is theta. The normal reaction is n. When the angular speed is 3/2 omega, the normal reaction becomes 1/2 n. Show that cos theta is equal to 4/9 cos alpha. So, first things first, we know that there will be some tensional force in the string. There will also be some tensional force here. And because the particle is in equilibrium, these two tensional forces will be the same. So, immediately we could recognize that tension must be equal to mg at B. So, it means that tension is given by 6/7 mg. This is our value for the tensional force. Now, what do we do with all this information? The most direct way to show the required result is to consider the horizontal motion of the particle at A. So what we need to remember here, so the force, if we resolve the forces horizontally, we should get that for the first scenario, T sine theta, which is the horizontal component of the tensional force, must be equal to the centripetal force experienced by A towards the center, which in this case is m omega squared r. What is r? So that's what we need to riddle out, because r is not given to us directly. The radius of this circle. If we look at the setup of the question, we know that this vertical distance here is h. This is given to us here in the question. This vertical distance here is h. And we know that our angle is theta. Therefore, this length here, which is r, our radius, is given by simple trigonometry, which show that it is h tan theta. So we can rewrite this first scenario as 6/7 mg sine theta is equal to m omega squared h tan theta. Likewise, if we consider the second scenario, we'll get that t sine alpha is equal to m omega squared r. And in this case, this is given by 6/7 mg sine alpha is equal to m by 9/4 omega squared h tan alpha. Right? If we call this equation 1 and we call this equation 2, dividing equation 1 by 2, so equation 1 divided by equation 2, this yields that sine theta over sine alpha must be equal to 4/9 tan theta over tan alpha. And if we cross multiply, we get that sine theta on tan theta must be equal to 4/9 sine alpha over tan alpha. Now, what is sine on tan? Sine on tan is actually cos. So we get that cos theta is equal to 4/9 cos alpha, which is exactly what we are required to show. Part B tells us now to find n in terms of m and g, and also to find the value of cos alpha. So in the first scenario, we considered the horizontal components at A. What we now need to consider is the vertical components, the vertical components of the force at A. So resolving vertically at A, what we should notice here, if we resolve vertically at A, we now have a normal reaction force N, we have the weight mg, and also we have the vertical component of the tensional force, which is T cos the angle here. So if we resolve vertically at A for our first scenario, we should get that T cos theta plus the normal reaction force is equal to mg. And in our second scenario, we get that T cos alpha plus 1/2 n is equal to mg. We also know from the first part that we just showed in part A that cos theta is 4/9 cos alpha. So if we rewrite equation 1 using this, so I can call this equation 1, I can call this equation 2. If we consider equation 1, we will end up with 4/9 cos alpha by T plus N is equal to mg. And from this, we can get that T cos alpha is equal to mg minus n divided by 4/9, which really means 9/4 by this. And all what is required for us to do now is to substitute this into equation 2 for T cos alpha. So we get from equation 2 now, we get that 9/4 mg minus n plus 1/2 n is equal to mg. This expanding and simplifying, this leads to minus 7/4 n is equal to minus 5/4 mg. Therefore, the normal force N is given as 5/7 mg. And that is N in terms of m and g. But we also have to find the value of cos alpha. So if we consider back equation 2, if we consider the rewritten form here, cos alpha is simply given as 9/4 mg minus n. N is 5/7 mg all over the value of t. Now what is t? T is 6/7 mg from the first part of the question. And this, once we simplify this, we should get that cos alpha is equal to 3/4. And that is question 6. And now the final question on the paper deals with momentum. So we are told here now that two uniform smooth spheres A and B of equal radii have masses m and 1/2 m respectively. The two spheres are moving on a horizontal plane when they collide. Immediately before the collision, sphere A is traveling with speed u, and its direction of motion makes an angle alpha with the line of centers. Sphere B is traveling with speed 2u, and its direction of motion makes an angle beta with the line of centers. The coefficient of restitution between the spheres is 5/8, and alpha plus beta is 90 degrees. Find the component of the velocity of B parallel to the line of centers after the collision, giving your answer in terms of u and alpha. So for spheres colliding at an angle like this, what we have to remember is momentum is conserved along the line of the centers. So, and also it's good here that we mention our directional notation. We can say that the direction, this direction is positive and this direction will be negative, remembering that velocity is of course a vector. So what we have to do is resolve this velocity u into its parallel and perpendicular components. The parallel component of the velocity is what we will use when applying the conservation of momentum along the line of centers. So the component here is u cos alpha, and similarly the component here will be 2u cos beta. So now if we apply the conservation of momentum, momentum before collision is equal to the momentum after the collision. Momentum is mass by velocity. So we get for A, mu cos alpha minus a half m into 2u cos beta is equal to mv1 plus 1/2 m v2, where v1 is the speed of A after the collision and v2 is the speed of B after the collision. This, if we divide throughout by m, this simplifies to u cos alpha minus u cos beta is equal to v1 plus 1/2 v2. So this is what we get from applying the conservation of momentum along the line of centers of the sphere. Now, we also have to make use of the restitution equation, which says that v1 minus v2 over u1 minus u2 is equal to minus e. In this case, v1 is the speed of A after the collision, so u1 is the speed of A before the collision. Likewise, v2 is the speed of B after the collision. u2 will be the speed of B before the collision. So if we apply this restitution equation here, we get that v1 minus v2 all over the initial velocity of u before the collision is u cos alpha minus the velocity of B before the collision, which in this case is minus 2u cos beta, and this is equal to minus e. And if we now cross multiply from this, we can get that v1 minus v2 is equal to minus eu cos alpha minus 2eu cos beta. Now what we are interested in is the velocity of B, so we need to find v2. So from this expression we can get that v1 is simply equal to v2 minus eu cos alpha minus 2eu cos beta. If we substitute now for v1 into this equation here, we obtain now that u cos alpha minus u cos beta is equal to v2 plus 1/2 v2 will become 3 onto v2 minus eu cos alpha minus 2eu cos beta. Now, we are told again in the question that the coefficient of restitution E is 5/8. Now, there's another important bit of information given to us in the question. They tell us that alpha plus beta is equal to 90 degrees. What is the significance of this? What we should recall from regular 9709 mathematics is that if this is true, it means that sine alpha is equal to cos beta. And similarly, that cos beta is equal to sine alpha. And what this means now is we can actually, wherever we see cos beta, we can replace it with sine alpha. So this becomes u cos alpha minus minus u sine alpha plus eu cos alpha plus 2eu sine alpha is equal to 3 onto v2. So if we simplify this up, we'll get that u cos alpha minus u sine alpha plus 5/8 by u cos alpha plus 2 5/8 by u sine alpha is equal to 3 onto v2. If we simplify all of this, what we'll end up with here is that u cos alpha plus 5/8 u cos alpha becomes 13 on 8 u cos alpha, and minus u sine alpha plus 10 on 8 u sine alpha becomes 1/4 u sine alpha. And this is equal to 3 on 2 v2. Therefore, we get that v2 is equal to 2/3, if we divide throughout by 3 on 2, 2/3 into 13 on 8 u cos alpha plus 1/4 u sine alpha. Good. Something now occurred to me here as well. Please be mindful of this. I realized what I did, I just restated what was here. The other alternative I meant to include is that this means that sine beta is equal to cos alpha. Right? My mistake there, my apologies. Now, the second part of the question tells us that the direction of motion of B after the collision is parallel to the direction of motion of A before the collision. Now, what is the direction of motion of A before the collision? So what we have to consider is the direction of motion here. What they are asking us for, and this is something to be aware of, the direction is given by Vy over Vx, which is the vertical component of the velocity, which in this case is the component perpendicular to the line of center, over the component of the velocity parallel with the line of centers, or along the line of centers. So if we look at it for A, we observe that the direction will be given by u sine alpha all over u cos alpha, which is equal to tan alpha. Right? This here is the direction of A before the collision. Now the direction of B after the collision will be the vertical, or the vertical component of the velocity divided by the horizontal component of the velocity after the collision. And remember that in these collisions, the vertical component of the velocity is unchanged. So the direction of B will be given by Vy over Vx. Vy in our initial case is 2u sine beta. What is Vx? Vx is the expression that we would have just found out in part A, which is V2. Now, if the directions are parallel to each other, it means that we can equate them to one another. So it means here that sine alpha, right, it means here that sine alpha over cos alpha, right, over cos alpha must be equal to 2u. Now this is important. Remember we just said, I just clarified that sine beta is equal to cos alpha. So we can replace sine beta with cos alpha is equal to 2u cos alpha all over the expression we just obtained, which is 2/3 into, we could also factor out the u, because there's a u common here, we can factor out the u. So we'll get 2/3 u into 13 on 8 cos alpha plus 1/4 sine alpha. The u's cancel off, and if we cross multiply everything together, we should get 13 on 12 sine alpha cos alpha plus 1/6 sine squared alpha is equal to 2 cos squared alpha. Right, and now what we can say here that we could write this over as 1/6 sine squared alpha plus 13 on 12 sine alpha cos alpha minus 2 cos squared alpha is equal to 0. Now the question asks us to find the value of tan alpha. So we need to introduce the tan function into this equation somehow. And to do that, we divide throughout by the highest power of the cos term, which in this case is cos squared alpha. So if we divide throughout by cos squared alpha, we get 1/6 sine squared on cos squared, which is 1/6 tan squared alpha, plus 13 on 12. Sine alpha cos alpha divided by cos squared leaves sine alpha on cos alpha, which is simply tan alpha minus 2 equals 0. If we multiply throughout by 12, we should get 2 tan squared alpha plus 13 tan alpha minus 24 equals 0. And now we can simply factorize this. So we get tan alpha plus 8, and we get 2 tan alpha minus 3 is equal to 0. So it means therefore that tan alpha is equal to minus 8, or tan alpha is equal to 3/2. However, remember that they told us in the question that alpha plus beta is equal to 90 degrees. This implies that alpha and beta must be acute angles. So this becomes invalid. So the only possible value for tan alpha, and this is important, we get two values of tan alpha. The question asks for the value of tan alpha. It used the singular, which is important in these maths questions from time to time. So the value of tan alpha, there's only one value we can take, and the value that we have to take here is that tan alpha is equal to 3/2. And that was the end of question number 7, and this was the end of the paper. So although the paper had a fairly, I would say, low grade boundary, that should not imply that it was a difficult paper. It was by no means that demanding of a paper. Perhaps the most difficult aspect of the paper is ensuring accuracy when working through all the algebra, because as we have seen, it's pretty algebraic. It's quite algebraic in nature. But once you were able to keep calm, you knew how to apply the relevant principles and be accurate with your algebra, this paper should not have been that big of a hurdle to cross. So I hope that this video was useful to some of you. And if there is anything that you want clarification on with the video, you can simply leave it in the comments down below. Be sure to subscribe, and until next time, thanks for watching, everyone.